Hello, everyone. My name is John, and today I'm going to share a pitch on my project that's close to my heart: the price of a home and the cost of bias. This project dives into something that we rarely ask in machine learning, not just whether a model is accurate, but whether it is fair. It's a story about housing, history, and hidden bias and what we can do about it. So let's begin with a question. There are two families, they live on the same street. Their homes have the same number of rooms, the same features, even the same school district. But one family lives in a majority black neighborhood. The price that an AI model predicts for their home is significantly lower, not because of the house, but because of where they live. It's not a bug, it's a bias. And it's not just theoretical, it's what happens when we train models on data shaped by inequality. So, when I talk about my motivation, I was inspired to explore this after reading Unmasking AI, a powerful book that shows how racial bias can hide inside algorithms. It made me wonder, what if the model we trust so much is already unfair? And if that is true, how would a machine learning model behave? Would it simply repeat injustice under the disguise of objective prediction? To explore this, I use the more prominent Boston housing dataset, one of the most well-known datasets in machine learning. It includes useful features like average number of rooms, distance to employment, school quality, but it also includes a feature called B. It's very controversial, which is based on the proportion of Black residents in a neighborhood. It's a relic of the 1970s and it's still being used in models today. My goal was to examine what happens when this feature is present. Does it subtly or significantly affect predictions? Yeah, so here's the risk. If Black majority neighborhoods have had historically lower prices due to redefining or systematic inequality, then the model might learn more Black residents tend to correspond to lower value. Not because it is true today, but because that's what the data shows from the past. And that's how discrimination enters silently to a model through some spreadsheet or CSV file. So how do we test fairness? I trained four popular regression models: linear regression, decision tree, random forest, and XGBoost. These are all commonly used in predictive tasks, especially housing. But rather than just measuring performance, I wanted to ask, are these models making fair predictions or just accurate ones? So to do this, I've used a powerful open source Python library called Dalex. Dalex doesn't just evaluate how well a model performs, it helps us interrogate whether a model is fair. It looks under the hood to assess bias, giving us fairness metrics based on academic definitions of equality in predictions. So Dalex helps us test three fairness conditions: independence, separation, sufficiency. So independence, are predictions influenced by the protected group like race? Separation, do prediction errors differ across groups? Sufficiency, if a model predicts the same value for two people, can we trust it equally for both? These are not just math tests, they reflect the ethical foundation of AI that serves everyone, not just the majority. So when we talk about the results, here's what I found. Linear regression failed the independence test. Its predictions were influenced by race. XGBoost, although it had the best accuracy, failed the separation test, meaning it treated different groups unequally when the actual outcome was the same. But decision tree and random forest models, they were accurate and passed all three fairness tests. This is critical. It shows that accuracy doesn't guarantee fairness. So what I learned is that AI accuracy does not guarantee fairness. Sensitive features like B can still quietly affect outcomes. It may or may not, but it's very essential that we check whether there is any kind of influence on the model. Even strong performing models like SGBoost can still show bias against certain groups. We need to audit every model we build, not just for performance, but for justice. In this case, the decision tree and random forest weren't just smart, they were fair, and that makes them more trustworthy. Here's the truth: a model that's 95% accurate but 100% unfair is still broken. We can't let algorithms inherit the bias of the past and disguise it as a prediction. Fairness isn't a feature, it's responsibility, and it's very essential that we use better systems. We have to focus on accuracy, but at the same time, it should be fair for everyone. Thank you.